Good morning, Code Milkers. Today's problem was search in rotated sorted array. Let's read the question. I already solved it because these are the medium level problems. I can't solve them in under 20 minutes or even 30 minutes, so to render them would take like 6 hours on my computer, and I've got better things to do than wait for the rendering to end. So suppose an array sorted in ascending order is rotated at some pivot unknown to you beforehand. So the array 0, 1, 2, 4, and so on may become 4, 5, 6, 7, 0, 1, 2. So basically, at this third index here at the 4, we are shifting all the elements before it to the end of the array, and then that new array is the one we're working with. Spoiler alert, the rotating doesn't matter for our solution. It's kind of a red herring. It determines how we solve the problem, but the general idea of it is the same as if it wasn't rotated. So you're given a target value to search for. If it's found in the array, return its index, otherwise return -1. This part's crucial. You may assume there are no duplicates in the array. That's important. And also, equally important, because it gives you basically the solution, is your algorithm's runtime complexity must be in the order of O log of n. Now, when you see this in relation to a sorted array, it's basically screaming at you to do a binary search. So if you don't know what a binary search is, essentially we have a sorted array, and we start at the middle index searching for a number, and depending on if our target is less than or greater than the middle element, we move to the left side of the middle or move to the right side and do the same operation on either side. And then so basically at each iteration, our search list is half the size of the last call, and then eventually we get down to 1 or 2 elements, and we can decide which one is the right one, or if the element doesn't exist at all in the list. How that's a little different with this problem, what makes it a little tricky, is that the array is sorted, but it might be rotated on a pivot. So we can't necessarily say that, like in this one, in this rotated example here, with 4, 5, 6, 7, 0, 1, 2, we would look at 7 and say, if we're looking for 0, we would look at the middle element 7 and say 0 is less than 7, so let's go to the left of it, because if it's ascending order, 0 will be before 7. But if we did that, we would end up in the array of 4, 5, 6, and we would never find the answer, even though 0 does exist. It's just in the wrong placement based on the pivot. So that affects how we do the binary search in this. Here we can see we got 2 examples. We have this input. We're looking for the element 0, and we return the index we find it at. In this example, we can see we're looking for a target 3, which does not exist in the array, so we return -1 after we exhaustively search each side of the array. So we need to do a binary search, which means we are halving the input array each time. But the other trick is that we need to maintain the indices of the original array so we can return it. Because if we don't keep a track of the indices, we will have to search for that element, which will end up taking a ton of time. So we could confirm that it exists with the binary search, but then we need to find the index. So it would defeat the point of the binary search. So essentially, what we're doing is, let me get out the whiteboard here. So I'll run you through an iteration of a problem with my solution. So let's say we have the 4, 5, 6, 7, 0, 1, 2. Okay. We start at 7, and 0 is less than 7, but we can't rely on it being actually before it. So what we're going to do is we're going to recurse on each slice of the array to the left and right of the middle index. So now we have 4, 5, 6. Wow, that is a great 4. Then we got 0, 1, and 2. Imagine there are commas between them. It's kind of hard to do commas with a mouse. So in here we look at the middle index 5, we look at the middle index 1. They're not the target, so we have to break it down further. We recurse again. We have 4, and we have 6. And we recurse further here. We have 0, and we have 2. Now, 0 obviously is our right target. Since we've been saving the indices, we can just return I. So return ret. There we go. I really need to get like a pen for this because I'd be surprised if any of you can even read that. Return the index, and all of these return -1. Then at the topmost recursion call, so where we initially called our function BS, that's what we shorten binary search to. We look at the left return value and we look at the right return value. If the left is not equal to -1, we return that one. But if it is -1, we by default return the right because we know that it's either -1 or it has the correct index. So this is a high level implementation view of what my algorithm does. So let's go back to LeetCode. So I'll run you through the code now. So we have our search function. It takes a nums and target. We don't need to worry about that. This is where, the rubber meets the road. We have our BS function, and it takes 2 inputs, low and high. So low is the lower end of the subarray we're going to look at, and high is the upper end of the subarray we're going to look at. Those represent the indices of the original array. So we're not modifying the array in place because then we won't know which index we need to actually return. It has to be unmodified. So here we compute the mid value, and for my purposes, if there's an even number of elements, I default to the first of the 2 middle values, and then the second subarray of that is longer than the first one. So I made that choice. You could do it. The second element is the middle. It's up to you. Here we're checking if the current element at the mid index is actually equal to target. We just return that index, and we don't need to recurse any further. We're good. Here we're checking if the array size is 2, because if the high value is 2 and the low value is 1 less than it, so 1 index lower, we know that there's only 2 elements in the sliced array. So there we just have to pick between one or the other. If one of them is the correct target, we return that, else -1. Here, if low is greater than or equal to high, we know that the array size is 1, because the low, if you can see here, how we're actually invoking the BS function is the high end, we subtract 1, and the right, we add 1 to the mid. So eventually, the low end will surpass the high end if we get further, if we get to the point where the array size has gone beyond 1, is at 1 element. So at that point, we know that the answer is not in there, return -1. And here are recursive calls to the left and the right side. And then here we just return the correct value. So if left is not equal to -1, we return left, which means that we found the target there. If left is -1, that means that only the right side could have the target. So we just return whatever right is. It could be -1, it could be 2, 3, 4, whatever the actual index is. Then here, this is in our search function. We're just returning the return value of the BS invocation, which starts at the first index 0 and sliced to the absolute end of the array, so the last index. We can see the time complexity here. Of course, it's O log of n. Put the binary search. It was accepted. And it beat 95%. Not bad. Okay. Hope this helped. Have a great day.